All right, let's play detective. Today, we're diving into a case where we have to figure out if we're dealing with a flat-out lie or just some really, really bad luck. So let's get right to the evidence. So here's the situation. We've got this basketball player, and he claims he's an elite 80% free throw shooter. That's his story. But the facts we've seen, the evidence, well, it tells a different tale. He only made 32 out of 50 shots. You do the math. That's just 64%. So who do you believe? His claim or the data? And this is what it all boils down to, right? There are really only two ways this could play out. One, he's the real deal, an 80% shooter who just had a terrible day at the office. I mean, it happens to the best of them. Or two, his claim is just bogus and his actual skill level is, well, lower than 80%. Our job is to figure out which story the evidence is pointing to.
To get to the bottom of this, we need to set this up like a proper investigation. We need to lay out the two competing ideas. In statistics, we call these hypotheses. You can think of it like a courtroom. You have the prosecution's story versus the defense's story.
And here they are. On one side, you have what's called the null hypothesis. Just think of this as the status quo, the innocent until proven guilty idea. It assumes the player's claim is true, his skill really is 80%. On the other side is the alternative hypothesis. That's our suspicion, right? That's the theory that his true percentage is actually less than 80%. So yeah, the null hypothesis, you'll see it written as H0, is always our starting point. It's the world where everything is exactly as claimed. Our whole mission is to see if we have enough evidence to cast serious doubt on this version of reality. And the alternative hypothesis, or HA, is our theory. It's the hunch that made us suspicious in the first place, that based on what we saw, he's just not an 80% shooter. This is the idea that we're looking for strong evidence to support. Okay, so we've got our two competing theories clearly defined. Now it's time to act like a jury. It's time to weigh the evidence. And the way we do this is by kind of playing devil's advocate. This right here, this is the absolute heart of the whole process. We're going to pretend, just for a second, that he's telling the truth. Let's live in the world where he is an 80% shooter. Now, in that world, how weird is it that he shot 64%? Is that a once-in-a-lifetime fluke, or is it something that could totally happen? And wow, this simulation just lays it all out for us. So imagine a computer programmed a true 80% shooter and then had him shoot 400 different sets of 50 free throws. Each dot is one of those sets. As you'd expect, most of the results are clumped right there around 80%. But then look, way over on the left. That's where our guy's 64% performance is. He's not just a little off, he's a massive outlier. Let's put a hard number on that. Out of those 400 simulations of the legit 80% shooter, a performance this bad, or even worse, only happened 3 times. 3! That's less than 1% of the time. The evidence against his claim is starting to look pretty darn strong. So this brings us to a fork in the road. We have to pick which story makes more sense. Story number 1. The player is an 80% shooter, and he just happened to have the unluckiest day of his life, hitting a 3 in 400 long shot. Or story number 2, which is a lot simpler. His claim is wrong, his real skill is lower, and that's why his 64% day wasn't that surprising at all. Statistics is just about figuring out which story is more believable. Now, to make that decision, we need one final piece of evidence. In our statistical investigation, this is the smoking gun. It's a single number that tells us exactly how strong our evidence is, and it's called the p-value. So what the heck is a p-value? Think of it as a probability, a weirdness score. It answers this one question. If the original claim is true, what's the chance of seeing a result as crazy as the one we just saw? Based on our simulation, you can probably guess this number is going to be pretty small. And there it is. The actual calculated p-value for our basketball player is 0.0075. Let's put that in plain English. That means there's only a 0.75% chance, not even a 1% chance, that a true 80% shooter would shoot this badly just because of random luck. That is incredibly unlikely.
And here's the bottom line, the simple rule of thumb. The smaller that p-value gets, the more trouble the original claim is in. A tiny p-value means we have very strong evidence. It's basically the data screaming at us that our result was super unlikely to happen if the original story were true. Okay, we've got our claim, we have our evidence, we have our smoking gun, the p-value. Now it's time to make a formal decision. It is time to deliver the verdict. Now, to make sure we're not just going with our gut, statisticians use a cutoff point they decide on before they even look at the data. It's called a significance level, or alpha. A really common one is 0.05, or 5%. Think of this as our line in the sand. If the chance of our result happening randomly is less than 5%, we're going to say it probably didn't happen randomly. And the rule for the verdict couldn't be simpler. If our p-value sneaks under that line in the sand, our alpha, we reject the original claim. The evidence is just too strong. If the p-value is bigger, we fail to reject it. And notice that phrasing. We don't say we accept the claim, we just say the evidence wasn't strong enough to knock it down. So, let's bring it home. Our p-value of 0.0075 is way, way smaller than our 0.05 line in the sand. So, the verdict is in. We reject the null hypothesis. We have convincing statistical evidence that this player's true free throw percentage is actually less than 80%. You know, this whole detective process we just walked through, it follows this really clean four-step method every single time. 1, you state the two competing theories. 2, you plan your test by setting your line in the sand. 3, you do the math and find that p-value. And 4, you conclude by delivering the verdict. State, plan, do, conclude. It's the playbook.
But hold on. Case closed, right? We got him. Well, not so fast. Just like in a real courtroom, a statistical verdict isn't 100% foolproof. It's all based on probability, which means there's always a tiny, tiny chance we got it wrong.
And there are two ways we could have messed up. First, there's a type 1 error. That's when we reject a claim that was actually true. It's like convicting an innocent person. Maybe he really was an 80% shooter who just had that 3 in 400 bad day. The other mistake is a type 2 error, and that's the opposite, failing to reject a false claim. That's like letting a guilty person walk free because we didn't have quite enough evidence.
And one last thing I really have to clear up. When you hear the phrase statistically significant, please don't think it means the result is important or a big deal. It's just a technical term. All it means is that what we saw was very unlikely to have happened just by random chance. That's it. And really, that's what this is all about. This whole process isn't about finding some kind of absolute 100% universal truth. It's about having a structured way to weigh evidence against a claim. It takes us from a simple gut feeling to a decision that's actually backed by probability. And it leaves you with a really personal question. Where do you draw your line in the sand? How much evidence is enough to convince you?